Hi, my name is Lydia Jones. This is for Chemistry 122, and I will be talking about the potential energy diagrams. So to start off, I wanted to be able to label the chart, just a blank chart for the potential energy diagrams. So starting off, I will be talking about each element of the actual diagram. One is one with a two-step mechanism, but I would just be using it to label it out, just the little steps as part of it. So starting off, the first part that I want to talk about is the activation energy, which is right here, activation energy. This little gap in between shows where the activation energy starts and where it ends at. This actual little dotted line right here shows where the original energy was, and where it is going to end up at ends right here actually. So at the left side, this part is the reactant. Whenever you're looking at an equation, usually the equation will be somewhere right here. Example from the notes, we use the one H3N touching nitrogen with a triple bond towards carbon. And from that, we get the products to be at the end. These are the end products down here. The little gap in between right here would be considered the delta H, which stands for the heat reaction. So I'll be putting that right here, delta H reaction. Depending on which way the actual diagram goes, either positive or negative, this could be positive or negative down here. But for this example, this one is a negative delta H reaction, which makes that exothermic. So I will just come down a little bit so I can show you guys what it would usually look like if it's exothermic or endothermic. So for example, say that the diagram looks like this. This is the reactions, and this is the products. Products. And the dotted line is right here to show where the energy started at, the activation energy. This little gap in between right here would make it negative delta H, just like the original example, exothermic, because it's going downwards. And for an endothermic reaction, say that the energy starts down here, it goes upwards and it levels out. So say that the dotted line is down here, and that the energy is going up from the original. And the activation energy. This would be a positive delta H reaction. So endothermic, taking in the heat. This is letting it go, this is taking it in. Back to the original diagram, the box up here will be talking about the transition states. For this example, with there being two, it will be these two up on top, right at the top. To go into further detail, with the example that I chose, this is a two-step mechanism. So I will be showing how there could be possibly a step 1 and a step 2. Step 1, step 2. That alone would show that there is two different activation energy areas. This will be number 1, and then this will be number 2. There's two different transition states. And for this example, the activation energy is the same, has the same constant rate, and it has about the same overall rate as well. I also want to talk about the thermal energy distribution. And I will draw a little diagram that looks kind of like what we learned. change the colors. So there are two different T's, T1 and T2. And that stands for temperature 1 and temperature 2. So for temperature 1, let's just make a diagram that kind of shows where it's at. T1. Let's choose a different color. And T2. As we talked about in class, as the temperature increases, the fraction of moles with enough energy to surmount the activation energy also increases. So around, and I also want to label the actual sides of the diagram. So this is more of like an exponential factor type of thing. Moving on, I also wanted to talk about catalysis. Catalysis of the actual diagram and how it will make it look different. I'll be drawing out what a possible diagram could look like and the difference between what a normal and a one with a catalyst would look like. Okay. Just to draw a normal one, I could do one that is doing from an exothermic reaction. So this is the one without a catalyst. So it takes the full time that it needs. And then for a catalyst, I would just use the color yellow. This is where there could be possibly a drop in the energy it takes to be able to finish the reaction. And it lowers the activation energy barrier. So this is the new transition state. Then there's a big gap in between from this to this. The reactants stay over here. Let me use a color so you can see a little bit better. And the products are still down here. But as you can see, the reaction process still takes the same amount of time, but it definitely lowers the amount of energy needed to finish this reaction. Another quick topic I wanted to talk about was the frequency factor. In which the frequency factor is the amount of approaches to the activation barrier. I'll write this down. And there's something that is important called a WAG, the actual approaching to the activation barrier. And an important part to remember is a lot of these do not have enough energy to get over the barrier. Well, okay. These are some of the different types of potential energy diagrams that we talked about. Just a little review. We talked about how there are reactants on one side, products on the other. It'll always be that way. If there is one transition state or two, it'll still be at the top line up here. There will be a gap in between the dotted line and the actual top of the transition state. That'll be the activation energy area right here. And the area between the either increased or decreased free energy, or just energy, just using this as an example, will be the positive or negative delta reaction, delta H reaction, which could be either exothermic, which is releasing energy, or endothermic, which is taking in energy. I hope I was able to explain some of the actual parts to the diagram, potential energy diagram, well enough, and I hope that this helps somebody actually be able to understand about the potential energy diagrams a little bit more. Thank you.